At the close of the 19th century, physics stood at what many believed was the peak of human understanding. The laws of nature appeared orderly, precise, and almost complete. For more than 2 centuries, classical physics had successfully explained the motion of planets, the behavior of falling objects, the flow of heat, and the nature of light and electricity. The universe seemed to operate like a perfectly constructed machine, governed by clear rules that could be expressed through elegant mathematical equations. Confidence among scientists was high, and there was a widespread belief that the fundamental principles of the physical world had already been discovered. This confidence was rooted primarily in the achievements of Isaac Newton and James Clerk Maxwell. Newton's laws of motion and gravitation had provided a powerful framework for understanding mechanics, from the swing of a pendulum to the movement of celestial bodies. His work suggested that if the forces acting on an object were known, its future motion could be predicted with absolute certainty. This idea of determinism became a cornerstone of classical physics. The universe was viewed as predictable, measurable, and fully knowable, provided that enough information was available. In the 19th century, Maxwell added another pillar to this structure by unifying electricity, magnetism, and light into a single theoretical framework. His equations showed that light itself was an electromagnetic wave, traveling through space at a constant speed. This discovery was seen as a triumph of human reason, further reinforcing the belief that nature's secrets were being steadily uncovered. By combining Newtonian mechanics with Maxwell's electromagnetic theory and the laws of thermodynamics, physicists felt they possessed a complete description of the physical world. Thermodynamics, in particular, played a crucial role in shaping scientific thought during this era. It dealt with heat, energy, and work, and introduced concepts such as entropy and the conservation of energy. These ideas were essential for understanding engines, industrial processes, and the behavior of gases. The laws of thermodynamics appeared universal and unbreakable, applying equally to steam engines and stars. Together with mechanics and electromagnetism, they formed a powerful trio that seemed capable of explaining nearly everything. As the 19th century drew to a close, physics textbooks reflected this sense of near completion. Some prominent scientists even suggested that future research would involve little more than refining measurements and calculating values to greater precision. The major laws were believed to be settled. Any remaining problems were considered minor puzzles rather than fundamental challenges. The foundations of physics, it was thought, were secure. Yet beneath this surface of confidence, cracks were beginning to appear. Certain experimental results stubbornly refused to align with classical predictions. These anomalies were initially treated as technical issues, expected to be resolved within the existing framework. However, as experiments became more precise, these discrepancies grew more troubling. They hinted that the classical view of nature might be incomplete or even flawed at a deeper level. One such challenge arose in the study of heat radiation. Scientists had long been interested in understanding how objects emit energy when heated. A so-called Blackbody was an idealized object that absorbed all incoming radiation and emitted energy solely based on its temperature. Experiments showed that the radiation emitted by such objects followed a specific distribution across different wavelengths. Classical physics attempted to explain this behavior using established laws, but the results were deeply unsatisfactory. According to classical theory, particularly the principles derived from electromagnetism and statistical mechanics, a heated object should emit more and more energy at shorter wavelengths. This prediction led to a mathematical result implying that an infinite amount of energy would be emitted in the ultraviolet region of the spectrum. This outcome was clearly absurd and contradicted experimental observations, which showed that energy emission peaked at a certain wavelength and then declined. This failure became known as a serious theoretical problem, even though its full implications were not yet understood. Another limitation of classical physics appeared in the study of atomic structure. Atoms were known to exist, and their behavior could be inferred from chemical reactions and gas laws, but their internal structure remained mysterious. Classical models imagined atoms as tiny solar systems, with electrons orbiting a central nucleus like planets around the Sun. However, according to classical electromagnetism, such orbiting electrons should continuously radiate energy and quickly spiral into the nucleus. Matter, as a stable entity, should not exist at all under these assumptions. Yet atoms were clearly stable, and matter persisted. Light itself also presented unresolved questions. While Maxwell's theory described light as a wave, certain experiments hinted at particle-like behavior. Phenomena such as the interaction of light with matter could not always be fully explained by wave theory alone. These inconsistencies did not yet point clearly toward a solution, but they suggested that the nature of light was more complex than previously believed. Even the concept of energy, so central to classical physics, began to show signs of strain. Energy was treated as a continuous quantity, capable of being divided into arbitrarily small amounts. This assumption worked well for large-scale phenomena, but became problematic when applied to microscopic systems. As scientists probed smaller scales and higher frequencies, classical ideas lost their explanatory power. Despite these growing difficulties, most physicists remained committed to the classical world-view. The success of existing theories in explaining everyday phenomena was overwhelming, and abandoning them seemed unnecessary and even reckless. The anomalies were viewed as isolated problems, not signs of a fundamental crisis. There was a strong reluctance to question the core assumptions of continuity, determinism, and classical causality. This intellectual atmosphere is crucial for understanding the significance of what was about to happen. The limitations of 19th-century physics were not immediately obvious as a revolutionary turning point. Instead, they appeared as small shadows at the edges of an otherwise brilliant picture. The scientific community stood confidently on a foundation that seemed unshakable, unaware that it was about to be transformed. The end of the 19th century was therefore a moment of both triumph and tension. On the surface, physics appeared complete, elegant, and unified. Beneath that surface, unresolved problems quietly accumulated, waiting for someone to take them seriously enough to challenge long-held assumptions. These limitations were not just technical flaws. They were signs that nature did not conform entirely to human expectations. It was within this context of apparent certainty and hidden crisis that the stage was set for a profound transformation. The old framework had reached the limits of its explanatory power. What was needed was not a minor adjustment, but a new way of thinking about energy, matter, and the laws that govern them. The confidence of classical physics, built over centuries, would soon give way to uncertainty, probability, and a radically different vision of reality. This transition did not happen overnight, but its origins lay firmly in the unanswered questions and limitations that defined physics at the end of the 19th century. As the 19th century moved closer to its end, the growing tension between theory and experiment became harder to ignore. Laboratories across Europe were producing increasingly precise measurements, and these measurements were beginning to expose the weaknesses of classical ideas. What once appeared as small irregularities now stood out as persistent contradictions. Physics, which had long prided itself on certainty, was quietly entering a period of doubt. One of the most unsettling aspects of this situation was that the problems did not arise from obscure or poorly understood experiments. Instead, they emerged from carefully controlled observations that were repeated and verified by multiple researchers. The failure of classical physics was not due to lack of effort or mathematical skill, but rather to assumptions that had gone unquestioned for generations. Concepts such as continuity, absolute time, and deterministic motion were so deeply embedded in scientific thinking that few considered the possibility that they might be incomplete. Statistical mechanics, a field developed to explain the behavior of large numbers of particles, also revealed troubling inconsistencies. While it successfully explained many properties of gases, it struggled when applied to radiation. The idea that energy could be freely shared among all possible modes of motion led directly to predictions that were physically impossible. This was not merely an error in calculation, but a sign that the underlying model of energy distribution was flawed. The conflict between theory and observation created a philosophical discomfort among physicists. Science had long been guided by the belief that nature followed simple, universal laws that could be discovered through reason and experiment. If these laws failed under certain conditions, what did that imply about the reliability of scientific knowledge itself? This question was rarely asked openly, but it lingered in the background, shaping the attitudes of those who worked at the frontiers of research. At the same time, new experimental techniques were allowing scientists to explore phenomena at smaller scales and higher energies than ever before. Spectroscopy revealed discrete lines in the emission and absorption spectra of atoms, suggesting that atoms interacted with energy in specific, fixed amounts. Classical physics, which allowed for smooth and continuous changes, offered no convincing explanation for these sharply defined patterns. The evidence pointed toward an underlying structure in nature that classical theory could not describe. The study of heat capacity provided another clue that something fundamental was missing. According to classical predictions, the heat capacity of solids should remain constant regardless of temperature. Experiments showed otherwise. At low temperatures, heat capacity dropped dramatically, contradicting expectations. Once again, classical physics failed precisely where experimental accuracy was greatest. These failures were not random. They followed a pattern, consistently appearing when systems were examined at very small scales or extreme conditions. Despite these warning signs, there was no immediate push to abandon classical ideas. The existing framework was simply too successful in everyday applications. Engineers relied on classical mechanics to build bridges and machines. Astronomers used Newton's laws to predict planetary motion with extraordinary accuracy. Electromagnetic theory powered the rapid expansion of communication technologies. The practical success of classical physics made its theoretical limitations easier to dismiss. There was also a cultural factor at play. Many physicists were trained within the classical tradition and had built their careers on its principles. Accepting that these principles might be fundamentally incomplete required not only intellectual flexibility, but also a willingness to question long-held beliefs. For some, this was an uncomfortable prospect. It was far easier to assume that the problems would eventually be resolved through minor adjustments. This resistance to change highlights an important aspect of scientific progress. Revolutions in science rarely occur because old theories are entirely wrong. Instead, they happen because old theories are incomplete. Classical physics was not useless. It was extraordinarily effective within a certain domain. The challenge lay in recognizing the boundaries of that domain and admitting that a new framework was needed beyond it. As the century ended, physics stood at a crossroads. On one path lay continued refinement of classical models, with the hope that existing problems could be solved without altering foundational assumptions. On the other path lay a more radical approach, questioning whether nature itself behaved according to rules that defied classical intuition. This second path was uncertain and risky, but it was increasingly supported by experimental evidence. The atmosphere of the time was therefore one of quiet anticipation rather than open crisis. Few physicists spoke openly about the possibility of a fundamental breakdown in theory. Yet many sensed that something important was approaching. There was a feeling that physics was on the verge of a transformation, even if its shape and direction were unclear. This moment of uncertainty was essential. Without it, the bold ideas that followed might never have been considered seriously. The limitations of 19th century physics created a space in which new concepts could emerge. They forced scientists to confront the possibility that nature did not conform to human expectations of continuity and predictability. The realization that classical physics had limits did not diminish its achievements. Instead, it placed them in a broader context. The laws discovered by Newton, Maxwell, and others remained valid for a wide range of phenomena. What changed was the understanding that these laws were approximations, not absolute truths. They described a particular layer of reality, not its deepest foundations. This shift in perspective prepared the scientific world for one of the most profound changes in intellectual history. The unresolved problems of the 19th century were not dead ends. They were signposts pointing toward a deeper theory. The failures of classical physics were not signs of defeat, but indicators of progress, revealing where old ideas reached their limits. As the new century approached, the stage was fully set. The tools of mathematics and experimentation were in place. The questions had been clearly defined, even if their answers were unknown. All that remained was for someone to take the decisive step, to propose an idea radical enough to resolve these contradictions. The transformation that followed would redefine concepts of energy, matter, and reality itself. It would replace certainty with probability and continuity with discreteness. But none of this would have been possible without the quiet crisis of the late 19th century. The limitations of classical physics were the necessary beginning of a new era, marking the end of one world, you, and the birth of another that would forever change how humanity understands universe. Max Planck's scientific background and mindset were shaped by a unique combination of tradition, discipline, and deep philosophical reflection. To understand how such a cautious and conservative thinker became the founder of the quantum era, it is necessary to look closely at the intellectual world that formed him and the personal attitudes that guided his work. His revolutionary contribution did not arise from a desire to overthrow existing ideas, but from a lifelong commitment to order, logic, and truth as he understood them. Max Carl Ernst Ludwig Planck was born in 1858 into an educated and respected German family. Scholarship and public service were part of his family heritage. His father was a professor of law, and academic discussion was a natural part of household life. From an early age, Planck was surrounded by an atmosphere that valued discipline, intellectual honesty, and respect for established knowledge. This environment played a significant role in shaping his character. He grew up believing that science was not merely a career, but a serious moral pursuit aimed at uncovering universal truths. As a student, Planck showed exceptional ability, but he was not initially drawn to experimental work. Instead, he was fascinated by theoretical ideas and the deep principles underlying physical laws. When he entered university, physics was not considered the most promising field, as many believed its foundations were already complete. In fact, Planck was advised by some senior scientists to choose a different discipline because physics offered little room for original discovery. Yet this advice did not deter him. He was attracted precisely by the idea that physics rested on firm, well-established principles. He wanted to understand these principles as deeply as possible, not replace them. Planck's early academic training took place in Munich and later in Berlin, where he studied under some of the most prominent physicists of the time. During these years, he developed a strong admiration for classical physics, particularly thermodynamics. Thermodynamics appealed to him because of its universal nature. Its laws did not depend on detailed models of atoms or molecules, which were still controversial at the time. Instead, thermodynamics dealt with broad, general principles such as energy conservation and entropy. Planck viewed these laws as absolute, almost philosophical truths about nature. This preference reveals much about Planck's mindset. He believed deeply in determinism and objectivity. For him, the laws of physics existed independently of human observers and were not subject to chance or randomness. Nature, in his view, followed strict rules, even if humans did not yet fully understand them. This belief aligned perfectly with classical physics, which portrayed the universe as a predictable system governed by precise mathematical relationships. Planck's doctoral work focused on the second law of thermodynamics, particularly the concept of entropy. At the time, entropy was often interpreted statistically, linked to the random motion of particles. Planck was uncomfortable with this interpretation. He preferred to think of entropy as an objective, fundamental property of nature rather than a result of probability or human ignorance. This discomfort with statistical explanations would later make his role in the birth of quantum theory all the more remarkable. Throughout his early career, Planck struggled to gain recognition. His work was highly theoretical and not immediately appreciated by the broader scientific community. Experimental physics was gaining prominence, and abstract theoretical research often seemed disconnected from practical results. Despite this, Planck remained committed to his approach. He believed that deep theoretical understanding would eventually prove its value, even if recognition came slowly. Planck's personality was marked by patience and perseverance. He was not a bold self-promoter, nor did he seek controversy. Instead, he valued careful reasoning and consistency. He was willing to spend years refining ideas rather than rushing to publish incomplete results. This methodical approach reflected his broader world view. For Planck, science was a gradual process of uncovering truths that already existed, not a creative invention driven by imagination alone. Another important aspect of Planck's mindset was his respect for authority and tradition. He held great admiration for earlier scientists and believed that new theories should build upon, rather than destroy, existing knowledge. This conservative attitude made him skeptical of radical ideas, especially those that challenged the foundations of classical physics. Even when experimental evidence suggested problems, Planck's instinct was to search for solutions that preserved established laws. This mindset explains why Planck did not initially see himself as a revolutionary. When he later introduced the idea of energy quanta, he did so reluctantly and viewed it as a mathematical convenience rather than a fundamental change in how nature behaves. In his own words, this step was an act of desperation, taken only because all classical approaches had failed to explain the data. His goal was not to create a new theory of physics, but to save classical physics from contradiction. Planck's moral and philosophical outlook also influenced his scientific thinking. He believed that science required humility. Human theories, in his view, were attempts to approximate an objective reality that might never be fully grasped. This belief allowed him to accept that even deeply trusted principles could be limited, though he did so cautiously and with great reluctance. Unlike younger physicists who would later embrace uncertainty and probability, Planck remained emotionally attached to certainty and order. Outside of science, Planck lived a life marked by discipline and personal tragedy. He was deeply committed to music and often played the piano, finding in music a sense of harmony and structure that mirrored his view of the universe. His personal life, however, was marked by profound loss, including the deaths of his wife and children. These experiences reinforced his belief in the existence of deeper laws governing reality, even when human life appeared chaotic and unjust. Planck's resilience in the face of personal hardship mirrored his approach to scientific challenges. He did not abandon his beliefs easily, but neither did he ignore evidence. When confronted with experimental results that contradicted classical theory, he did not dismiss them outright. Instead, he worked tirelessly to reconcile theory with observation, even if it meant temporarily stepping outside his philosophical comfort zone. By the late 1890s, Planck had established himself as a respected but not extraordinary figure in the scientific community. He was known as a reliable and rigorous theorist, particularly in thermodynamics. No one, including Planck himself, expected him to initiate a scientific revolution. He represented continuity rather than change, stability rather than disruption. This is precisely what makes his later role so historically significant. Planck's background had trained him to trust universal laws, to value mathematical elegance, and to believe in the ultimate rationality of nature. These qualities equipped him to recognize when something was fundamentally wrong. While more radical thinkers might have dismissed anomalies as experimental errors, Planck took them seriously because they threatened the internal consistency of physics. His respect for order made inconsistency intolerable. As he approached the problem of radiation, Planck brought with him all these intellectual habits. He did not question classical physics lightly. Every step away from it caused discomfort, yet his integrity as a scientist prevented him from ignoring the failure of existing theories. This tension between loyalty to tradition and commitment to truth defined his mindset at the moment when history would later judge him as a revolutionary. The irony of Max Planck's scientific background is that it was precisely his conservative nature that enabled his breakthrough. Because he believed so strongly in absolute laws, he was willing to make a radical assumption to preserve them. He did not abandon the idea of order. Instead, he redefined it in a way he did not fully understand at the time. The concept of quantized energy emerged not from a desire for novelty, but from a refusal to accept contradiction. In this way, Planck's mindset stands as a powerful example of how scientific revolutions often begin. They are not always led by those who seek to destroy the past, but by those who respect it so deeply that they are willing to confront its limits honestly. Planck's background gave him the tools, discipline, and moral seriousness required to take that step. As the 20th century dawned, Planck remained, at heart, a classical physicist. Even as younger scientists built quantum mechanics on the foundation he had laid, he struggled to accept some of its implications. Yet without his careful reasoning, his patience, and his philosophical commitment to universal laws, the quantum era might never have begun. The story of Max Planck's scientific background and minds, it is therefore not just a biography of a physicist, but a lesson in how knowledge advances. It shows that progress often arises from tension between old beliefs and new evidence, and that even the most conservative thinkers can change the world when they remain faithful to truth above comfort. As Planck moved deeper into his professional career, his scientific mindset became even more firmly anchored in the values of precision, patience, and intellectual responsibility. By the 1890s, he had secured a respected position in Berlin, one of the most important centers of scientific research in Europe. His lectures were known for their clarity and rigor, and his colleagues viewed him as a dependable authority on thermodynamics. Yet beneath this stability, Planck was engaging with problems that would quietly test the very foundations of his beliefs. What distinguished Planck from many of his contemporaries was his unusual relationship with uncertainty. While he disliked probabilistic explanations, he did not deny their usefulness outright. Instead, he treated them as temporary tools, useful for calculation, but not reflective of ultimate reality. For Planck, probability signaled incomplete knowledge, not fundamental randomness. This distinction mattered deeply to him and shaped how he approached unsolved problems. He believed that behind every statistical pattern lay an exact law waiting to be discovered. This belief guided his work on radiation theory. When experimental data began to show clear discrepancies with classical predictions, Planck did not accuse the experiments of being flawed, nor did he rush to invent speculative models of atoms. Instead, he approached the problem with the same mindset he had applied to thermodynamics, searching for a universal principle that could restore harmony between theory and observation. His goal was consistency, not innovation for its own sake. Planck's sense of scientific duty also played a critical role. He believed that a physicist had an obligation to follow evidence wherever it led, even if the conclusions were uncomfortable. This sense of duty restrained him from ignoring inconvenient results, but it also prevented him from embracing radical interpretations too quickly. He occupied a narrow path between skepticism and openness, moving forward only when logic demanded it. During this period, Planck was deeply influenced by discussions with experimental physicists who were measuring radiation spectra with unprecedented accuracy. These experiments left little room for doubt. The classical formulas simply did not work. For a man who believed in the internal coherence of physical law, this failure was intolerable. Nature, he was convinced, could not be self-contradictory. If the mathematics produced nonsense, then one of the assumptions must be wrong. Yet abandoning an assumption was no small matter. The idea that energy was continuous had been fundamental to physics for centuries. It was not merely a technical detail, but a reflection of how scientists imagined change itself. Continuous energy meant smooth transitions, predictable behavior, and mathematical elegance. Discreteness, by contrast, seemed artificial and inelegant, more like a bookkeeping trick than a physical reality. Planck shared this prejudice strongly. When he finally introduced the idea that energy could only be emitted or absorbed in discrete amounts, he did so with hesitation. He did not present it as a bold new vision of nature, but as a formal assumption that allowed the equations to work. In his own mind, this step did not contradict his philosophical beliefs, because he did not yet interpret quanta as real. They were, to him, a temporary scaffold supporting a classical structure. This cautious interpretation reveals how deeply Planck's mindset differed from that of later quantum physicists. Where others would see quanta as evidence of a fundamentally probabilistic universe, Planck saw them as a mathematical necessity imposed by human limitations. He believed that a deeper, deterministic explanation would eventually emerge, restoring continuity at a more fundamental level. In this sense, Planck never fully embraced the philosophical consequences of his own discovery. Even after his work gained recognition, Planck remained intellectually conservative. When Einstein proposed that light itself consisted of quanta, Planck supported the mathematical correctness of the work, but resisted its physical interpretation. He accepted that energy exchange might be quantized, but struggled with the idea that light, long understood as a wave, could behave like a particle. This hesitation was not due to stubbornness, but to his commitment to coherence and conceptual clarity. Planck's interactions with younger physicists further highlight his mindset. He encouraged rigorous thinking and respected originality, yet he remained wary of speculation unsupported by strong evidence. Figures such as Einstein, Bohr, and Sommerfeld admired Planck deeply, even when they moved beyond his philosophical comfort zone. They saw in him a model of scientific integrity, someone who valued truth over personal pride. Another defining feature of Planck's character was his resilience in the face of historical turmoil. Living through the First World War and later the rise of the Nazi regime, he experienced profound moral and personal challenges. His loyalty to Germany conflicted with his commitment to universal scientific values. Despite immense pressure, he defended academic freedom and the international nature of science whenever possible. These experiences reinforced his belief that science must be guided by principles that transcend politics and ideology. Personal tragedy continued to shape Planck's outlook during these years. The loss of his children, including the execution of his son for involvement in a plot against Hitler, left deep emotional scars. Yet even in grief, Planck maintained his belief in the rational structure of the universe. He did not see science as a source of comfort, but as a discipline that demanded honesty regardless of personal suffering. This stoic attitude mirrored his approach to scientific problems: endure uncertainty, trust in deeper order. As quantum mechanics developed rapidly in the 1920s, Planck watched with mixed emotions. He recognized the power and success of the new theory, yet he struggled with its departure from determinism. The idea that physical outcomes could only be predicted probabilistically challenged his lifelong belief in strict causality. Nevertheless, he did not oppose the new generation. Instead, he acknowledged that their work was necessary and valuable, even if it conflicted with his philosophical instincts. This willingness to accept progress without fully agreeing with it is one of the most admirable aspects of Planck's mindset. He did not cling to authority or attempt to suppress ideas that contradicted his own preferences. He understood that science advances through dialogue and generational change. His role, as he saw it, was not to dictate the future, but to ensure that it was built on rigorous foundations. Looking back, it becomes clear that Planck's mindset was defined by a rare balance of humility and conviction. He believed deeply in objective truth, yet he acknowledged the limitations of human understanding. He trusted mathematical structure, yet he respected experimental fact above theory. He valued tradition, yet he did not allow it to override evidence. These qualities made him uniquely suited to stand at the threshold between classical and modern physics. The second keynote of Max Planck's life, his scientific background and mindset, therefore cannot be separated from his achievement. His discovery was not an accident, nor was it the product of reckless imagination. It emerged from decades of disciplined thinking, philosophical reflection, and moral seriousness. He was prepared, intellectually and emotionally, to recognize the limits of classical physics precisely because he understood it so deeply. In the broader history of science, Planck represents a crucial type of thinker. Not the flamboyant revolutionary, but the careful guardian of consistency who recognizes when the old structure can no longer stand unchanged. His mindset shows that revolutions in knowledge often begin with loyalty rather than rebellion, with respect rather than rejection. By the time of his death in 1947, Planck had witnessed the full transformation of physics. The quantum era he helped initiate had reshaped science and technology beyond anything he could have imagined in 1900. Yet his personal world remained rooted in the values of order, reason, and universal law. This tension between his inner convictions and the external consequences of his work is what makes his story so compelling. In the end, Max Planck's scientific background and mindset teach a profound lesson. True commitment to truth sometimes requires stepping into uncertainty, even against one's own preferences. Planck did not abandon his principles. He followed them to their logical conclusion. In doing so, he opened a door that others would walk through, transforming our understanding of reality. The Blackbody radiation problem emerged quietly but persistently in the late 19th century, becoming one of the most serious challenges to classical physics. It began as an attempt to understand something seemingly simple: how objects emit energy when they are heated. Physicists were not initially searching for a revolution. They were trying to describe a well-defined experimental phenomenon with mathematical precision. Yet this problem would expose deep flaws in existing theories and ultimately force a radical change in the way energy and matter were understood. A blackbody is an idealized object that absorbs all incoming radiation and reflects none. When heated, it emits radiation solely based on its temperature, not its shape, material, or surface properties. This made blackbody radiation an attractive subject for study because it appeared to follow universal laws. Experiments showed that as a blackbody's temperature increased, it emitted radiation across a range of wavelengths, producing a characteristic curve. The intensity rose with decreasing wavelength, reached a peak, and then fell off sharply at shorter wavelengths. Classical physics attempted to explain this behavior using established principles of electromagnetism and thermodynamics. According to these theories, radiation inside a cavity could be treated as standing electromagnetic waves. By applying statistical mechanics, physicists tried to calculate how energy should be distributed among these waves. At low frequencies, the predictions matched experimental data reasonably well. However, as the wavelength decreased and frequency increased, the theory produced results that diverged dramatically from reality. The classical calculation suggested that energy should increase without limit at shorter wavelengths. Mathematically, this meant that a blackbody should emit an infinite amount of energy in the ultraviolet region of the spectrum. This prediction was not just inaccurate, it was physically impossible. Experiments showed no such runaway increase. Instead, radiation intensity dropped rapidly at high frequencies. The stark contrast between theory and observation revealed a fundamental failure of classical assumptions. This contradiction became known as the ultraviolet catastrophe. The term itself reflected the severity of the problem. It was not a small error that could be fixed by adjusting a parameter or refining a model. It was a complete breakdown of the theory when applied to high-frequency radiation. The catastrophe forced physicists to confront an uncomfortable reality. The most trusted laws of physics were producing nonsense under conditions that should have been well within their range of validity. What made the Blackbody radiation problem particularly troubling was its clarity. The experimental results were reliable and reproducible. The mathematics was sound. The failure lay not in technique, but in the conceptual foundation of the theory. Classical physics assumed that energy could be exchanged continuously, in arbitrarily small amounts. This assumption had worked well for mechanical systems and low-frequency phenomena, but it led directly to the ultraviolet catastrophe when applied to radiation. Several scientists attempted partial solutions. Some formulas fit the data at low frequencies, while others worked better at high frequencies. However, these were empirical fixes rather than true explanations. They lacked a coherent theoretical basis and did not address the underlying issue. The problem remained unresolved, hanging over physics as an open wound that could not be ignored. The Blackbody radiation problem was more than a technical puzzle. It was a sign that classical physics had reached its limits. It demonstrated that the laws governing macroscopic objects could not simply be extended to microscopic processes without contradiction. Energy exchange at very small scales behaved differently than expected. This realization marked a turning point, even though its full implications were not immediately understood. For Max Planck, the problem carried special significance. As a theorist deeply committed to thermodynamics and universal laws, he found the inconsistency intolerable. Nature, he believed, must be internally consistent. If classical assumptions led to infinity and contradiction, then at least one of those assumptions had to be wrong. The Blackbody radiation problem forced him to reconsider the nature of energy itself, something few physicists were willing to do at the time. In this sense, the Blackbody radiation problem served as the gateway to the quantum era. It exposed the inadequacy of continuity as a universal principle and opened the possibility that energy might be exchanged in discrete steps. While this idea initially appeared unnatural and even absurd, it resolved the contradiction perfectly. By limiting how energy could be distributed at high frequencies, the catastrophic divergence disappeared. The importance of the Blackbody radiation problem lies not only in its solution, but in what it revealed about scientific progress. It showed that even the most successful theories have boundaries. When those boundaries are crossed, nature does not compromise to fit human expectations. Instead, understanding must change. The Blackbody radiation problem was the moment when classical physics encountered a wall it could not pass, and in doing so, it pointed toward a deeper and more accurate description of reality. Introduction of energy, Quanta marked one of the most profound shifts in the history of science, redefining how physicists understood the exchange of energy at the most fundamental level. This idea did not emerge from a desire to challenge tradition, but from a careful and reluctant response to experimental evidence that could no longer be explained using classical assumptions. The concept of quanta arose as a solution to a specific problem, yet its implications extended far beyond its original context. Before this development, energy was universally treated as a continuous quantity. According to classical physics, energy could be divided into infinitely small portions, flowing smoothly from one system to another. This view was deeply embedded in scientific thinking and aligned well with everyday experience. Whether considering the motion of objects, the flow of heat, or the propagation of waves, continuity seemed natural and unquestionable. There was no obvious reason to suspect that energy behaved differently at microscopic scales. However, the Blackbody radiation problem challenged this assumption directly. When classical theories were applied to radiation, they led to predictions that contradicted experimental results. The failure was not subtle, it was dramatic. The mathematical framework, though logically consistent, produced infinite energy where none existed. This suggested that the error did not lie in the calculations, but in one of the underlying assumptions. The most vulnerable assumption was the continuity of energy exchange. Max Planck approached this dilemma with caution. His goal was not to overturn classical physics, but to preserve it by finding a modification that would restore agreement with experiment. In 1900, he proposed a radical idea. Energy could only be emitted or absorbed in discrete amounts. These amounts were proportional to the frequency of the radiation involved. The constant of proportionality, now known as Planck's constant, set the scale at which these discrete effects became significant. This proposal introduced the concept of energy quanta. Instead of flowing smoothly, energy was exchanged in small packets. An oscillator could not emit or absorb just any amount of energy. It had to do so in fixed steps. This single assumption was enough to eliminate the ultraviolet catastrophe and produce a formula that matched experimental data perfectly across all wavelengths. At the time, Planck viewed this step as a mathematical device rather than a statement about physical reality. He believed that the quantization of energy was a formal trick, useful for calculation, but not necessarily reflective of how nature truly behaved. In his mind, a deeper, continuous explanation might eventually be found. Nevertheless, the success of his formula forced the scientific community to take the idea seriously. The introduction of energy quanta challenged more than just a technical detail. It questioned a fundamental aspect of how change occurs in nature. Discreteness implied limits. It suggested that certain processes could not happen gradually, but only through sudden transitions. This idea was difficult to accept because it conflicted with intuition and with centuries of scientific tradition. Yet it was supported by experimental evidence in a way that could not be ignored. The significance of energy quanta became clearer as other physicists began to apply the idea to different phenomena. Einstein used the concept to explain the photoelectric effect, showing that light itself could behave as if it were composed of particles. This step went beyond Planck's original intention and suggested that quantization was not just a property of matter interacting with radiation, but of radiation itself. The boundaries of classical physics continued to shrink. What made the introduction of quanta especially revolutionary was that it altered the relationship between theory and reality. Classical physics aimed to describe nature in continuous terms, using smooth functions and deterministic laws. Quantum ideas introduced discontinuity and suggested that nature operated in steps rather than flows. This did not merely add a new concept, it required a new way of thinking about physical processes. Despite its revolutionary implications, the idea of energy quanta was initially met with skepticism. Many physicists resisted it, viewing it as an artificial construct with no physical meaning. Acceptance came gradually as more phenomena were successfully explained using quantum concepts. Each success weakened the classical world, and strengthened the case for a fundamentally new framework. The introduction of energy quanta stands as a turning point because it was the first clear break from classical continuity. It showed that the microscopic world obeys rules that differ from those governing everyday experience. Energy, once thought to be infinitely divisible, was revealed to have a granular structure under certain conditions. In retrospect, this idea marks the true beginning of the quantum era. It provided the seed from which quantum mechanics would grow, reshaping physics in the 20th century. The concept of energy quanta did not replace classical physics, but it defined its limits and revealed where a deeper theory was required. Ultimately, the importance of this keynote lies in its demonstration of how scientific understanding evolves. When evidence contradicts expectation, even the most basic assumptions must be reconsidered. The introduction of energy quanta was not a rejection of reason, but an extension of it, guided by experiment and enforced by logic. It opened a new path for physics, one that continues to shape our understanding of the universe today. The birth of quantum theory in 1900 marked a decisive moment in the history of physics, even though its revolutionary nature was not immediately recognized. At the time, it appeared to be a narrow solution to a specific technical problem rather than the foundation of a new world view. Yet this moment quietly transformed the direction of science, introducing concepts that would redefine how nature is understood at its most fundamental level. In December 1900, Max Planck presented a paper to the German Physical Society in which he introduced a new formula for Blackbody radiation. The formula matched experimental data with remarkable accuracy, resolving a problem that had resisted classical explanation for years. What made this achievement extraordinary was not merely its success, but the assumption on which it rested. Planck had proposed that energy exchange between matter and radiation occurred in discrete units rather than as a continuous flow. This proposal represented a radical departure from classical physics. For centuries, physical theories had been built on the idea of continuity. Motion, energy, and change were all thought to occur smoothly. Planck's assumption challenged this deeply ingrained belief, even though he himself did not initially grasp its full implications. In his view, the quantization of energy was a formal hypothesis, adopted reluctantly to make the mathematics work. Despite Planck's caution, the year 1900 is widely regarded as the birth of quantum theory because it introduced a fundamentally new principle. For the first time, a physical law explicitly depended on the idea that nature operates in discrete steps. This was not an approximation or a secondary effect. It was central to the theory's success. Classical physics could not reproduce the same results without encountering contradictions. The immediate reaction of the scientific community was mixed. Some physicists admired the mathematical elegance of Planck's formula, while others viewed the underlying assumption with suspicion. Many believed that quantization was a temporary measure that would eventually be replaced by a more satisfying classical explanation. There was little sense at the time that a new era had begun. Instead, Planck's work was seen as an ingenious but isolated fix. Over the following years, however, the significance of Planck's idea began to grow. As experimental techniques improved, more phenomena emerged that could not be explained by classical physics. The success of Planck's formula suggested that quantization was not an accident, but a clue to a deeper structure of nature. The notion that energy levels might be restricted rather than continuous started to gain credibility. The birth of quantum theory was therefore not a sudden explosion, but a gradual awakening. Planck's 1900 paper planted a seed that others would cultivate. When Albert Einstein applied the idea of quanta to light itself in 1905, the scope of the theory expanded dramatically. Light, long understood as a wave, was shown to exhibit particle-like behavior. This step confirmed that quantization was not limited to matter, but was a universal feature of energy exchange. What makes the birth of quantum theory especially significant is that it emerged from necessity rather than speculation. Planck did not set out to invent a new physics. He was driven by a commitment to consistency and by respect for experimental evidence. When classical assumptions failed, he adjusted them just enough to restore agreement with observation. This pragmatic approach gave the theory a solid foundation, even if its philosophical meaning remained unclear. The year 1900 also marked a shift in the relationship between theory and experiment. Classical physics often relied on intuitive models and continuous variables. Quantum theory, by contrast, was born from a formula that worked even when its interpretation was uncertain. This reversal challenged traditional ideas about how scientific understanding progresses. It suggested that mathematical structure and empirical success could precede intuitive explanation. As quantum theory developed, its consequences became impossible to ignore. The discrete nature of energy exchange explained atomic stability, spectral lines, and later the behavior of electrons and photons. Each new success reinforced the idea that Planck's original assumption reflected something real about the physical world. What began as a mathematical hypothesis gradually transformed into a new conceptual framework. The birth of quantum theory in 1900 thus represents more than a historical date. It marks the moment when physics crossed a boundary, moving beyond the limits of classical thought. The certainty and continuity of the 19th century gave way to a new vision of nature, one governed by probabilities, discrete states, and fundamental limits. In retrospect, the quiet presentation of Planck's paper stands as one of the most important events in science. It reminds us that revolutions do not always announce themselves loudly. Sometimes they begin with a simple equation, proposed cautiously, that changes everything. The birth of quantum theory was such a moment, opening a path that would reshape physics, technology, and our understanding of reality for generations to come. The initial resistance to quantum ideas and their eventual acceptance reveal how deeply scientific beliefs are shaped by tradition, intuition, and philosophical comfort. When Max Planck introduced the concept of energy quanta, it did not immediately transform physics. Instead, it unsettled a community that had long trusted the continuity and determinism of classical laws. The journey from skepticism to acceptance was slow, complex, and marked by debate, confusion, and gradual realization. At the start of the 20th century, classical physics had an extraordinary record of success. Its predictions were accurate, its mathematics elegant, and its principles intuitive. For many physicists, there was little motivation to abandon a framework that worked so well across so many domains. The idea that energy could only be exchanged in discrete units seemed artificial and unnecessary, especially since it conflicted with everyday experience. Resistance was therefore not merely emotional, but rational within the context of existing knowledge. Max Planck himself embodied this hesitation. Although he introduced quantization, he did not believe it represented a fundamental feature of nature. He hoped that future developments would restore continuity and determinism. This ambivalence influenced how others viewed the idea. If the originator of the concept treated it as a mathematical trick, there was little incentive for the broader community to embrace it fully. The resistance also had philosophical roots. Classical physics was grounded in the belief that nature was continuous and predictable. Quantum ideas threatened this world by introducing limits and discontinuities. The suggestion that physical processes occurred in jumps rather than smooth transitions felt conceptually disturbing. It raised uncomfortable questions about causality and the completeness of physical laws. Many scientists were reluctant to accept such implications without overwhelming evidence. Early quantum concepts also lacked a coherent theoretical framework. Planck's hypothesis explained Blackbody radiation, but it did not offer a general theory of matter and energy. Without a unifying structure, quantization appeared as an isolated anomaly rather than a guiding principle. This fragmentation made it easier to dismiss quantum ideas as special cases rather than signs of a deeper revolution. Acceptance began to grow as independent evidence accumulated. Albert Einstein's explanation of the photoelectric effect provided strong support for quantization. His work showed that light could behave as if it consisted of particles, each carrying a discrete amount of energy. This result could not be explained by classical wave theory and offered compelling proof that quantization was physically real, not merely a mathematical convenience. Further support came from studies of atomic spectra. Experiments revealed that atoms emit and absorb light at specific frequencies, producing sharp spectral lines. Classical models could not account for this discreteness. When Niels Bohr introduced a model of the atom based on quantized energy levels, it successfully explained these spectral patterns. Although Bohr's model was incomplete, its empirical success strengthened the case for quantum ideas. As these successes accumulated, resistance gradually weakened. What had once seemed unnatural began to appear necessary. The repeated failure of classical explanations forced physicists to reconsider their assumptions. Quantization was no longer an optional hypothesis, but an essential feature of any theory that aimed to describe atomic and subatomic phenomena accurately. The process of acceptance was not uniform. Some physicists embraced quantum ideas enthusiastically, while others remained skeptical for decades. Debates over interpretation were intense and often philosophical. Questions about the role of probability, measurement, and reality itself divided the scientific community. Acceptance of the mathematical formalism did not always mean acceptance of its implications. The turning point came in the 1920s with the development of quantum mechanics. The work of Heisenberg, Schrödinger, and others provided a consistent and powerful framework that unified earlier quantum concepts. Quantum mechanics not only explained known phenomena, but also predicted new effects that were later confirmed experimentally. Its success made resistance increasingly untenable. By this stage, acceptance was driven less by philosophical agreement and more by practical necessity. Quantum mechanics worked. It allowed physicists to calculate atomic behavior with unprecedented accuracy. Technologies based on quantum principles began to emerge, further reinforcing its validity. The debate shifted from whether quantum theory was correct to how it should be interpreted. The journey from resistance to acceptance illustrates a fundamental pattern in scientific progress. New ideas are often judged not only by evidence, but by how well they fit existing worldviews. When they challenge deep assumptions, acceptance takes time. Quantum theory forced physicists to rethink the nature of reality itself, and such a shift could not happen overnight. In the end, quantum theory prevailed not because it was comfortable, but because it was unavoidable. The accumulation of evidence left no alternative. What began as a reluctant hypothesis became a cornerstone of modern physics. The initial resistance and eventual acceptance of quantum ideas highlight the tension between tradition and innovation, showing how science advances through struggle as much as through discovery. Long-term impact of quantum theory on modern science and technology is one of the most far-reaching consequences of any scientific breakthrough in history. What began as an abstract attempt to explain radiation at the atomic level eventually reshaped nearly every branch of science and transformed daily life in ways that are often invisible but deeply fundamental. The ideas that emerged from the quantum revolution did not remain confined to theoretical physics. They became the foundation of the modern technological world. In science, quantum theory fundamentally changed how matter and energy are understood. It provided a precise explanation for the structure of atoms, revealing why electrons occupy specific energy levels and why atoms emit light at characteristic frequencies. This understanding laid the groundwork for modern chemistry, allowing scientists to explain chemical bonding, molecular structure, and reaction mechanisms at a fundamental level. Without quantum theory, chemistry would remain largely descriptive rather than predictive. Quantum mechanics also transformed the study of materials. The electrical, magnetic, and thermal properties of solids could only be fully explained through quantum principles. Concepts such as energy bands and electron spin revealed why some materials conduct electricity while others act as insulators or semiconductors. This insight did not merely deepen scientific understanding. It opened the door to entirely new classes of materials engineered for specific purposes. The technological consequences of these discoveries are immense. One of the most significant outcomes is the development of semiconductors. Quantum theory explains how electrons move through solid materials and how their behavior can be controlled. This knowledge made it possible to design transistors, which form the basic building blocks of all modern electronics. Computers, smartphones, and the Internet itself depend on devices whose operation is governed by quantum laws. Another transformative application is the laser. The principle behind lasers relies directly on quantum energy levels and stimulated emission, a process that cannot be described by classical physics. Lasers are now used in medicine, industry, communication, and entertainment. From eye surgery and barcode scanners to fiber optic networks, laser technology has become an essential part of modern infrastructure. Quantum theory has also had a profound impact on medical science. Imaging techniques such as MRI rely on quantum properties of atomic nuclei and their interaction with magnetic fields. These technologies allow doctors to see inside the human body with extraordinary detail, improving diagnosis and treatment while reducing the need for invasive procedures. Nuclear medicine, radiation therapy, and advanced imaging all trace their origins to quantum principles. Beyond technology, quantum theory has reshaped scientific thinking itself. It introduced a new understanding of reality in which probability replaces certainty and observation plays an active role in measurement. This shift influenced not only physics, but also philosophy, challenging traditional ideas about determinism and objectivity. The quantum world view revealed that nature at its deepest level does not always conform to everyday intuition. In recent decades, quantum theory has continued to drive innovation through emerging fields such as quantum computing and quantum communication. Quantum computers exploit superposition and entanglement to perform certain calculations far more efficiently than classical machines. Although still in development, this technology holds the potential to revolutionize fields such as cryptography, materials science, and drug discovery. Once again, ideas that once seemed abstract are becoming practical tools. The influence of quantum theory extends even to cosmology and our understanding of the universe as a whole. Models of stellar evolution, nuclear fusion in stars, and the behavior of matter under extreme conditions all rely on quantum physics. Without it, modern astrophysics would be impossible. The life cycles of stars, the formation of elements, and the energy of the sun itself are governed by quantum processes. What makes the long-term impact of quantum theory especially remarkable is that it emerged from a modest and cautious beginning. Max Planck did not foresee smartphones, lasers, or quantum computers. Yet his initial step revealed a deeper layer of reality that continues to shape scientific progress more than a century later. This illustrates how fundamental research, even when motivated by narrow questions, can lead to transformative outcomes. The legacy of quantum theory also serves as a reminder of the power of human curiosity and intellectual honesty. By accepting that classical ideas had limits and being willing to explore unfamiliar concepts, scientists opened a path to extraordinary advances. The quantum revolution shows that understanding nature at its most basic level can produce benefits that reach far beyond the laboratory. In the end, the long-term impact of quantum theory lies not only in the technologies it enabled, but in the way it changed humanity's relationship with the universe. It revealed a world richer, stranger, and more subtle than previously imagined, and in doing so, it expanded both scientific knowledge and human possibility.